Next is describing networks. A number of measures can be used to describe the structure of a network as whole, that is degree distribution, density, connectivity, tie strength and trust. What is degree distribution? Degree is used to describe the individual nodes. Degree distribution gives an idea of the degree of all the nodes in the network. To create a degree distribution, calculate the degree of each node in the network. The next step is to count how many nodes have each degree. This is total for each node, including those for which there are no nodes with that counter. Further, degree distribution is visualized using bar graph. The x-axis has the degrees as ascending order and y-axis indicates how many nodes have a given degree. So for example, if we take this, then first we have to calculate the degrees for each node. So A has 3 degrees, 1, 2, 3. Likewise, B has 4, C has 4, D has 5, E has 4, F has 5, G1, H1, I1, J2, K3, L3, M2, N1, O3, P9 and Q5. These are what? These are the number of degrees which each node has. Now, this is the first step. In the second step for degree distribution, we need to count how many times did 1 come, how many times did 2 come, how many times did 3 come, how many times 4 came, 5 came, 6 came, 7 came, 8 came, 9 came. Because here the highest is 9, so we have to calculate how many times till 9 each of them have come. So for example, 1 has come 1, 2, 3, 4 times. So we'll write 1 has come 4 times. Then 2 has come 1, 2 times. So we'll write 2 has come 2 times. Then 3 has come 1, 2, 3, 4 times. So we'll write 3 has come 4 times. Then 4 has come 1, 2, 3 times. So 4 has come 3 times. 5 has come 1, 2, 3 times. So 5 has come 3 times. 6 has come 0, 7, 0, 8, 0 and 9 we have 1 time. So 9 we have written 1 time. Now here there is x-axis and y-axis. This is the second step. In the third step for degree distribution, we draw a bar graph. In the bar graph, we have an x-axis and a y-axis. X-axis is the degrees, that is from 0 to 9, and number of nodes is there in the y-axis. Here the highest is 4, so we'll write 0 to 4. Now 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 has come how many times? 4 times. So this goes like this till 4. Then 2 has come 2 times. 3 has come 4 times. 4 has come 3 times. 5 has come 3 times. 6, 7, 8, 0 times. 9 has come 1 time. This is the way the plotting will happen. This is the way we have to solve sums on degree distribution. Next is density A. Another way to understand both individual nodes and the network as a whole is by studying density. Density describes how connected a network is. It is a statistics comparing the number of edges that exist in a network to the number of edges that could possibly exist. Consider the following two networks which both have the same number of nodes. Network A has very few edges while network B has numerous edges among the same number of nodes. Therefore, density of network B is higher. So, if you see, for example, this is what they have explained in the previous slide. Here you can see there are lot many edges. So, density of B is higher as compared to density of A. There is a simple formula for compounding the number of possible edges. If there are 8 nodes in a network, each node can connect to 7 other nodes. This scenario is known as the handshake problem. If there are 8 nodes in the network and each node can connect to 7 other nodes, then there are 8 into 7, 56 possible edges. For a network with n nodes, there are n into n minus 1 edges. Each node can connect with every other node excluding itself. So if there are 8 nodes, it can connect to 7 nodes. Each node can connect with every other node excluding itself. In case of undirected networks, there can be only one edge between the two nodes. So for directed networks, the formula says number of possible edges in the graph with n nodes is n into n minus 1. With n nodes and e edges, the formula for density calculation will be E, that is number of edges, divided by n number of nodes into n minus 1. For undirected, we have to divide it by 2. N into n minus 1 divided by 2, number of possible edges, and E divided by n into n minus 1 divided by 2. So consider the figure 3.6. Both have 8 edges. Here we see that there are 1, 2, 3, 4, 5, 6, 7, 8. Total there are 8 nodes. Both have 8 nodes. Network A has 5 edges. 1, 2, 3, 4 and 5. We see 5 edges are there. Since it is undirected, the formula will be given as, so it is an undirected network, the density is given as this formula, that is n, density is E upon E is 5 upon total number of nodes is 8 into 8 minus 1 divided by 2. E is edges is 5. So answer is 0.179. Network B has 16 edges. Since it is an undirected network, the density can be given as, so here we see 16 edges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So total 16 edges are there. So 16 edges upon total number of nodes 8 into 8 minus 1 divided by 2. Answer is 0.571. So network B is denser because 0.571 is greater than 0.179. So density of B is more than density of A. This is the way we have to calculate densities. Density, a network with no edges would have density 0. The densest possible network would be a network with all possible edges forming a clique. For a clique, the density will be 1. The density is always between 0 and 1, where 0 is the lowest possible density and 1 is the highest. So always remember, density answer will come between 0 and 1 whenever we are calculating it. Next is density in an ecocentric network. Computing the density of each node's ecocentric networks gives us a way to compare nodes. Some nodes will have dense ecocentric networks, which means a lot of friends know each other. Others will have sparse ecocentric networks, which means their connections do not know each other. The density of an ecocentric network is also referred to as local clustering coefficient. To compute the density of an ecocentric network, we use the 1.5 diameter network. For this calculation, the ego node will be excluded and we are interested in the connection between the nodes' friends. So consider node B, which is connected to A, C, H and F. If we want to calculate the density of this, the 1.5 ecocentric network of B, while by excluding B. So here we have written that we will exclude that because we are concerned with the node's friends. So it will be AC. The diagram will be like this after we exclude B. So the density of the graph is calculated as follows. Number of edges is 1, 2, 3, 4. Number of nodes is 4. Number of edges is 1, 2, 3, 4, 5. So we'll write number of edges e divided by n into n into n minus 1 divided by 2. E is 5 upon n is 1 2 3 4. 4 into n minus 1 3 divided by 2. 2 1s are 2 2s are 2 3s are 6. 5 divided by 6, which is 0.833 is the density of node B. Calculate the density of a ecocentric network. Next is connectivity. Connectivity, also known as cohesion, measures how the degrees are distributed in a graph. Connectivity is the count of the minimum number of nodes that would have to be removed before the graph becomes disconnected. So before the graph becomes disconnected, the minimum number which you have to remove. So if this is an example, the connectivity of the given graph is 1. Since we remove either node B or C or D, the graph will get disconnected. If you remove B, suppose this B is removed, you will get A and the other part will be over here. If you remove C, you will get this A and B, other will be here. If you remove D, this will be one part, this will be the other part. So in whichever ways, if you remove these three nodes, means any one node, your graph will be disconnected. So what is connectivity? How much number of nodes you have to remove for making the graph disconnected. This is the second example. Let's see this. The connectivity of the given graph is 2. In this, removing one node would not break the graph into two parts. Why? Because if you remove this node, A is still connected over here. You remove this, then also you have no disconnection. So at least you need to remove two nodes. So if you remove this and this both, then only A will be drawn apart and the other part will be like this. Similarly, B is also connected to 2, C is also connected to 2, D is also connected to 2. So whenever every node is connected to 2, by removing only one edge, the graph will not become disconnected. So minimum you need to remove both the edges. Next is centralization. It uses the distribution of a centrality measure to understand the network as a whole. Only one centrality is used at a time when computing centralization. If one node has extremely high centrality, while most other nodes have low centrality, the centralization of a graph is higher. If centrality is more evenly distributed, then the centralization of the network is low. Centralization is computed by looking at the sum of differences in the centrality between the most central node and every other node in the network and dividing this by maximum possible difference in centrality that could exist in the graph. So centralization is, let C of n be the centrality of node n using whatever centrality measure we choose. Say n asterisk is the most central node. We want to find the difference in centrality between n and every other node in the network and add those up. If there are n nodes in the network, the formula will be summation of C of n star minus C of I. Then we want to divide this by the sum of maximum possible differences between n and other nodes. So first we calculate this, then we calculate max of the maximum possible difference. We divide it by the sum of maximum possible difference.